in the classroom. We just stopped. We were like, we're doing nothing else, but we're watching this press conference. And you know how 14-year-olds reacted to it when they announced it? Woohoo! Strunk, why are we watching this? Did a miserable job. I did not talk once in school. They get it now. It was worse though a year later when I told them I was going to work for Ligo. And they go, Ligo? All right, no way. All right. So my name is Amber. I am the Education Outreach Coordinator here. That means I do all kinds of things, from lead tours and give talks to every once in a while they let me help replace a laser or something. So I do a wide variety of things. I've also enlisted a couple of our fellows here. We've got Ethan and Adrian. Some of you were on a tour with Adrian to answer some questions for us as well. So once we get finished with the talk, we're going to try to go for 30 minutes. We'll definitely answer questions along the way. If I can't answer them, hopefully one of these two can for you. We'll be good. And then we'll do a tour after. So how many of you did not go on one of the early tours and are here for the late tour? Perfect. If we are not done right at 3:30, don't freak out. I'm your tour guide. So it will not go out without me, okay? We always get people who pop up and run outside. They're like, am I missing it? You're not. It's me. You're good. All right, so let's check a little bit. I know some of you watched the video, but just because some of you may not have, let's do the brief who we are, what we do. Our name is LIGO. We are the Laser Interferometer Gravitational Wave Observatory. And now you will know why we say LIGO, because it's a mouthful. That's a really big thing to say. And 2 of the 4 words make sense, right? We've all seen a laser. We've made our cat, dog, little brother, sister, somebody chase it. And we know what an observatory does, right? We observe things. Those are questions. We observe things. And in particular, observatories observe space, right? This is still true of us. We still observe space, but we're doing it in a whole new way. We don't own a telescope. We use an interferometer. We don't use light. We use gravitational waves. And that's where we're unique. That's where we're different. So let's talk about gravitational waves first, so we have any idea what we're dealing with here. And you'll notice that I'm totally still a teacher. I'm going to make you answer me questions. So, what is gravity? Not a trick question. It makes things accelerate. Sweet.
Force equals mass times acceleration.
F equals ma. Yes. Remember, your teacher did good.
It's a geodesic along space-time.
Oh, it's a geodesic along space-time. What does that mean? Yeah, so, listen, you have been told, since you're about this high on, that gravity is a force that pulls you to the ground, right? And that the Earth is pulling you down. That's why you stay on the Earth, yeah? That's most of the story we hear. And the person who told us this was Newton. About 350 years ago, he came up with this idea. But did most of you know that Newton didn't like this idea? Even Newton thought this didn't make sense. He said, anybody who believes this has no faculty in thinking. He basically called you all stupid. Because we believed our teachers. He didn't like the idea that there's this invisible force that acts immediately over space. But what Newton said is, okay, the math makes sense, and I'm just going to accept it and move on. We still don't fully know what gravity is. We today have no idea what gravity actually is. And to me, that's fascinating. So we do use a different description, though, and that came from Einstein 100 years ago, right? So Newton's one description, it's wonderful, it got us to the moon 50 years ago, but we need Einstein to talk about what we do here. And Einstein's idea goes back to this geodesics. If we have space and time, the stars move in, forward, backwards, side to side, up, down, and time, they're connected. They're not separate. If you affect space, you affect time. And if you put a mass in the middle of this space-time, you get a warp. Okay? And that warp results in what we call gravity. It's not a force. Nothing is pulling you down. The Earth is not pulling on you. You're not pulling on the Earth. There's just a warp in space-time. Makes perfect sense, right? Didn't make sense to a lot of people in 1915 either. And they all thought Einstein was a little bit crazy at first. Most of them did. But let's think about it from a very easy point of view. Why does this look like gravity? Take a big trampoline, set you in the middle of a trampoline. And you warp the trampoline, right? I put a marble on top and let go. What happens to my marble? It rolls to you. It just follows a curve in the trampoline to you, right? If you jump, no force pulls you down. You just follow a curve in space-time back to the Earth. The difference is I can see the trampoline, I can't see the curve in space-time. That's all gravity is in Einstein's view. Okay? nice way to look at gravity, and it results in some very crazy things, such as, if space works, what happens to time? It has to work too, right? It's connected. And that means your second is not the same as a second for an astronaut on the International Space Station. They're vastly different seconds. So that's cool. But it also results in light bending, which we proved in 1919 by looking at a solar eclipse. Light bends around space-time as well. Helps us use GPS. GPS doesn't work without this time dilation thing we just talked about. And it also predicts gravitational waves. Yay, we're finally back to Ligo. Gravitational waves were thought to be an algebraic mistake. They come out of general relativity. Einstein thought they were an algebraic mistake, checked his math, and by 1918 said, nope, they're real, but you're never going to find them. Don't bother to try, you can't find these things. What do? They come from the fact that if you've got us going around the sun, we're warping that space-time, right? And that warp changes. And as you go around, ripples start to come off. You lose energy, and it comes off. And that energy warps space-time itself. And if that wave went straight through you, and it does about once every 15 to 30 minutes, makes you a little bit thinner and a little bit taller. Bad news, it makes you a little bit shorter and a little bit wider next. And it keeps doing that. It stretches and squashes space-time itself as it ripples through space-time. You, me, the Earth, everything it goes through. And that's really amazing. So, some scientists thought, well, even though Einstein said you can't find them, we'll think of a way. How could you find these? Well, you can imagine if I put a big ring on the ground, I could watch the stretching and compressing, and I could see the gravitational wave pass, right? It'd go from a circle to an oval, and I'd be pretty obvious, yeah? Circles are expensive. So, what if we just use an L? If we just put a big L on the ground, we could do the same thing. Look for that arm to get bigger and smaller, and we could see a gravitational wave. That was Ray Weiss's idea in 1972, one of the founders of Ligo. But you got to be able to measure that arm length change. So he suggested using a laser, an interferometer. Take the laser, put it on a beam splitter, half the light goes down one arm, half the light goes down the other arm. They hit mirrors on the end and come back. All we're doing is using light as a ruler. When that light comes back, it merges again at that beam splitter, and it interferes. Just like water waves interfere, it interferes. And it cancels itself out, and you get nothing. You get dark. But as the gravitational wave passes, it changes the length of the arm. And it changes the way the light lines up. And now you get bright spots, dark spots, bright spots, dark spots. That tells us our arm length change. That tells us the gravitational wave passed. And now we've detected gravitational waves. Make sense? All we're doing. Simple, right?
Yeah.
Devil's always in the details. There's a few extra mirrors we're not telling you about here, because you got to be really, really, really sensitive. You can't just make a tabletop interferometer. Most interferometers were like room size, maybe 40 meters. You can't detect gravitational waves with 40 meters. There's such small waves, you need really long arms. You actually need 4 kilometer or 2.5 mile long arms to see this. Okay? So that's how big this has to be. Nobody has ever built a device this big before. But our founders were able to go to Congress and convince them to give them money to not detect anything. I'm really amazed. They literally walked in and said, listen, we want to detect these things that Einstein says you can't find. We need a detector that's not going to detect anything because we don't have good enough technology. But if you give us that detector, we will tell you a few things. And we'll build new technology, better lasers, better mirrors, better coatings. And then, in about 15 years, we can put a new device in. You have to give us more money for that. And then we might see gravitational waves. That worked. And so they got money in the late 1980s, early 1990s. They started building in 96. They were operational by 2000. By 2015, we got our first detection. It took that long. 72 Ray wrote the paper, think about that. 1972, Ray Weiss wrote the paper. It wasn't until 2015 when he was vindicated that this worked. It's pretty cool. And he stuck with it that long. He's still with Ligo. He still comes in. He still does things every now and then. He's at MIT though, so we don't always see him here. You might notice there's 2 of us. We get tumbleweeds, they get trees and alligators. They're in Louisiana, but they're our twins. same device, same lasers, same coatings, we're the same. Because if you're gonna tell people you detected something that nobody ever detected before, that nobody thinks you can detect, probably gonna have two people seeing it, right? So you really needed verification that we saw it. We also use that to be able to get some kind of direction. These are just some images, so I'm gonna kind of flip through them quickly, but this is our laser. The entire table is our laser. The laser in my hand is a milliwatt laser, 0.001 watts. Coming off this table right now is about 30 watts of laser. You can pop balloons with like a 1 watt laser. In the arms, this light bounces, and it gets up to hundreds of kilowatts of laser. Longer arms mean more sensitivity, more laser power makes more sensitivity. There's a problem with more laser power. Heat is one. It makes thermal noise, so it makes your atoms move around more. But did you know that light can push things? There's something called radiation pressure. Our laser is strong enough that it can push our 88-pound mirrors. That mirror can be pushed by our laser if you turn it up high enough. So part of the reason why we're not have more laser power now, we have to deal with this thermal coating issue, and we have to deal with radiation pressure. Amazing to me that light can shove 88-pound mirror. Beautiful. This is one of our mirrors. It's connected to another glass blank by glass fibers. These glass fibers are 0.4 millimeters thick. Did you guys see it out there? If you didn't, go see it because it's beautiful. If you were on the tour already, the person sitting in the operator chair, Travis, he's one of the few people in the world who knows how to weld these. He welds these on for us. We have to be this sensitive. So remember those 2.5 mile long arms, those 4 kilometer long arms. When a gravitational wave passes, this is how much it changes by. There's a centimeter. Look at one hair on your head, that's how big it is. There's an atom, there's a nucleus, there's us. Our 2.5 mile long arms are changing less than the size of a single proton. That's an insane level of sensitivity. Makes it insanely hard to do what we do because every single vibration bothers us. If you all walked in the control room and jump up and down, they're going to yell and scream and kick you out. Because that matters. The trucks on the highway, did you guys notice that beautiful, smooth road? Isn't that a great road? As Hanford workers go to work, Monday through Thursday in the morning, hundreds of cars back to back on that road make enough vibration that we can't see as far into space. It reduces our sensitivity because of just the cars driving by. All right, so there's those two. We are at 3,000 kilometers apart, 1,800 miles from there to there. Gravitational waves travel at the speed of light. That means they go 3 times 10 to the 8 meters per second, or 187,000 miles a second. Which means from here to here takes 10 milliseconds maximum. If we see something that's greater than 10 milliseconds difference, we both see it, it's not a gravitational wave. It's got to be within 10 milliseconds. Okay? So one of the ways we can verify that that's what we're seeing. And on September 14th, 2015, we saw the very first gravitational wave, and this is what we saw. Aren't those beautiful, pretty squiggly lines? Do you understand why my 14-year-olds were a little underwhelmed when this graph came up? They're like, okay, yeah. I'll tell you why, as the teacher, I was not underwhelmed. Even though I didn't fully understand what was going on, here's what I did see. Do you see how beautiful those two things match? 3,000 kilometers apart, and in the real world, that's hard. We got the exact same signal. You'll notice the red one's a little bit taller. That's Hanford, that's us. There's a reason. Livingston saw the gravitational wave first. 7 milliseconds later, we saw it, but we were more sensitive. So they may have saw it first, but we saw it better. But we did get the exact same wave, and 0.2 of a second. Do you see the time axis down there? This gravitational wave lasted for 0.2 of a second. That's it. So what did we see in 0.2 of a second? Oh, sorry, that resulted in a Nobel Prize. Oh, I'm missing a slide. All right, it resulted in a Nobel Prize. But let me tell you what we saw anyway. We saw 2 black holes. Those pretty squiggly lines can tell you all of this. 2 black holes that were 30 times the mass of our sun. Okay? They were orbiting around each other. They were a couple hundred kilometers apart at this point. Okay? And as they start orbiting in, they get faster and faster and faster and faster because they're getting closer and closer and closer. Think of an ice skater who brings her arms or his arms in, right? They spin out. Same thing's happening. These black holes that are 30 times the mass of our sun are going 90,000 miles a second before they slam into each other and make a black hole that's 60 times the mass of our sun. In that process, 3 times the mass of our sun was converted to energy. 3 times our sun went from mass to pure energy that rippled through space-time for 1.3 billion years before hitting our detector in Livingston, Louisiana, and 7 milliseconds later hitting our detector here. When those 2 black holes collided, there were single cellular life forms on Earth. By the time they got to us, we got to a point where we could actually detect them and understand what the heck hit us. That's amazing to me. You can see why I got the Nobel Prize. So just so you know who's up here, this is Ray. Ray was the one who wrote the paper in '72. He fully won half the Nobel Prize for this. This is Barry Barish. Barry was responsible for our collaboration. He came in kind of later and he helped bring our collaboration together. And this is Kip Thorne. Of the 3, Kip is usually the name some people know because he's written a few popular books. He has something to do with the movie Interstellar. More than something, a lot to do with the movie Interstellar. So he's a little bit more famous than some of the other ones are. Kip was one of the first people on this as well. So Ray went to Kip. Kip was the one who thought of theoretically what could we see with these. Okay. I do have to stop here for a moment and say I hate this picture. I love all 3 of these guys. They're wonderful. Especially if you ever get a chance to hear Ray talk, go. He will amaze you. He's hilarious. He's wonderful. These 2 are great, but I love Ray. I'm not biased at all. But here's why I hate that picture. It gives the wrong impression about science. Ray wrote the paper in 1972. That picture is from 2017. Do you think he looked like that when he did the science? No. Science is done by these people over here. See these young guys doing science? It's not done by 3 old white guys. I mean, they did great science, but they weren't 3 old white guys at the time. They were 3 young white guys. But also, remember how some of you were in my group and I said we had 1,300 people in our collaboration, 20 countries, 101 institutions. We have a wide variety of people who do LIGO science. I encourage you to do 2 things. One, if you go out this door and take a left, you'll see this whole wall of pictures. Those are the people who work just here at LIGO Hanford. There are people like that all over the world working for us, doing what we do. Also, if you go to Humans of LIGO, you will see them profile different people in our collaboration. From Kip, he's on there, to the raven who was causing our noise. If you don't know that story, ask me. To all our graduate students and scientists and people across the board who do LIGO. These 3 will tell you they did not do LIGO on themselves. These 3, in every speech you hear from the Nobel Prize, said that they didn't do this. 1,300 people around the world did this. And that's important to know. Science is usually not done by 1 or 2 people anymore. That might have been the case 100 years ago. It's usually done by a large collaboration now. Speaking of collaborations, there's us 2, but we also have other detectors around the world, either functioning or coming. So we work with these folks. They're not part of LIGO, but we're collaborating with them. There's Virgo outside of Pisa, Italy. They're a 3-kilometer long detector, slightly different suspension, and they helped see a really important event in 2017. There's Geo 600 outside of Hanford, Germany. They're much, much smaller. They're 600 meters. They likely won't detect anything. Maybe a supernova if they're lucky. But they pilot things for us. Something like our squeeze light started at Geo 600 before it got implemented in LIGO. COGRA is just about operational. In the next 6 to 8 months, COGRA should be up and taking data, which is wonderful. They're in Japan. They're in a mine. They're using sapphire mirrors and cryogenically cooling their mirrors. They're doing some cool stuff.
How long?
3 kilometers as well. They're 3 kilometers. LIGO India is coming. LIGO India, they have purchased all the land. It's a yellow stick in the ground that says LIGO right now. But they will break ground soon, and they believe they'll be operational by 2025. That is the goal, to be operational. Okay. LIGO India has LIGO in their name for a reason. We are much more closely related to them. We have all the parts for a 3rd interferometer sitting right here at the Hanford site. Those will all get shipped to LIGO India. India is providing all the funding for the people, the buildings, all of that India is doing. LIGO is providing the parts, so they're much more intimately related to us. I'm going to tell you one last story and then we're done. I told you that Virgo was important in a detection 2 years ago that was important. On August 17th of 2017, we got a signal. This is our signal that we got. It was much longer than the signal we saw from the black holes. And we thought it looked interesting because longer means lower mass. So we had a good inclination that this was a really low mass. Either the smallest black holes we've ever seen or possibly neutron stars. Neutron stars are amazing because they're really, really dense, crazy objects. They're also remnants of dead stars. But they're so dense that the protons and neutrons protons and electrons have all come down into just neutrons. They collapse into each other into neutrons. And you take about 2 times the mass of our sun, and you put it between us and Richland. That's how dense they are. 1 tablespoon weighs as much as Mount Everest. And they have matter, and when they collide, you get light. So we were excited because black holes don't give off light, you only see gravitational waves. These might be neutron stars. We found out 1.7 seconds later, Fermi telescope got a gamma ray burst in the exact same patch of sky. Right where we thought we saw this merger, they thought they saw it. Let's skip over this. So see that big blueberry? That's Fermi. They said that's where it was. See these like bananas? The light green bananas is where Ligo told you it was. The dark green bananas where Ligo and Virgo told you it was. Within 11 hours of us telling electromagnetic astronomers, light astronomers, to look, they found it. See that little black dot? Remember how exciting those little pretty squiggly lines were? Everybody has my little black dot. It's gorgeous. Within 11 hours, we found that little black dot. And that little black dot is way cooler than what it looks like. Because what that is the remnant of 2 neutron stars colliding. And it's not really black. It actually was very bright blue when we found it. And it faded down through all parts of the electromagnetic spectrum. All the way down into radio waves, and was giving radio waves off for months, years after. Okay? And all of these little blue dots are all the EM astronomers around the world and in space that turned and looked. It was so important that fully 1/3 of the world's astronomers turned and looked at this event. That's how important it was. And you can actually see it fade. So there it is. It's fading down through the colors over several days. Okay? It was next to a galaxy that has been known since the 1700s. The galaxy NGC 4993. Beautiful name. Roll up. The astronomers like names. And this is what really happened. From all that data we can put together and do this simulation that tells you what happened. These neutron stars were orbiting. They were putting off gravitational waves. They merged and put off a gamma ray burst. And then this is that little black dot you saw. Now, this is a simulation, but we can model all the colors that was there. There was also a burst of X-rays that came that we believe is the collapse of the core into a black hole. This solved a couple of things. For many, many years, people didn't know where gamma ray bursts came from. There's predictions about where some of them came from. We now can tell you for certain that some portion of short gamma ray bursts are coming from neutron star mergers. We didn't know that before 2 years ago. Has anybody ever been told you're stardust? Had a teacher, professor, somebody tell you you're stardust? Some of you, yes? Okay. So, we say this, I like to say it to kids, we're stardust. Because all the atoms in your body, hydrogen and helium, were mainly from the Big Bang, but the rest of the atoms in your body are mainly from fusion inside of stars. And when they die, that gets dispersed through the universe, and you're made up of that, okay? We've known that for a long time, that makes sense. But that only works up to about iron on the periodic table, which is number 26. There's like 118-ish elements, right? So what happens from 26 to 118? That, you're usually told, comes from supernova. That when a star explodes and dies, we get enough energy to make all the rest of those. And astronomers have known for a while that's not true. It cannot add up for all the gold and platinum and uranium you see on Earth. You can't make that in supernovas. They've known that for a while. And they had a prediction that maybe, if neutron stars collided, that's where you could get enough energy and enough neutrons to make the rest of those elements. We didn't know for sure until August 17, 2017. 2 years ago, we were able to watch that light curve, model it, and see how much is being produced. So remember that little black dot? Let's go back to it because it's gorgeous, right? You guys know my black dot? About 200 Earths worth of gold were created in that little black dot. Kind of a cooler black dot now, right? I figured this is how we're going to fund space travel. Tell rich people. Don't tell them how far away it was. It's about 120 million light years away, so, but still. All right, with that, I'm going to go ahead and take some questions, so, yeah.